In this lecture, I am explaining how to draw the state diagram for a sequence detector that detects a required sequence. First of all, let us see what is meant by a sequence detector. Sequence detector is a finite state machine that receives an input bit stream and generates the logic high output whenever the required sequence is detected. There are two types of sequence detectors. Number one, Moore machine, and number two, Mealy machine. So here a more finite state machine has further two types, that is non-overlap type and overlap type. And also here Mealy finite state machine has two types, non-overlap type and overlap type. Now let us see here more finite state machine. Here, in order to draw the state diagram of a sequence detector, which is of more finite state machine type, here we need to follow 3 points. If you understand these 3 points, it is very simple to draw a state diagram. Let us now consider more finite state machine. So under this first point is number of states equal to number of bits of the given sequence plus 1. So now second point, non-overlap type. Suppose if it is a non-overlap type, we have to do something here, that is compare the last bit of the last state. See here, compare the last bit of the last state with the 1 bit state. If it is matched, then move the directed state transition line to that 1 bit state. Okay. Suppose if it is not matched, then we have to move the directed state transition line to reset state. Reset state is nothing but the initial state or ideal state or starting state. Third point, if the given sequence is overlap type sequence, then we have to follow this point. For 1 bit overlapping, compare the last 2 bits of the last state with the 2 bit state. If it is matched, then move the directed state transition line to the 2 bit state. Okay. If it is not matched, then compare the last bit of the last state with the 1 bit state. If it is matched, then move the directed state transition line from the last state to that 1 bit state, or else move the direct state transition line to the reset state. So this is for overlap type. Similarly, for 2 bit overlapping, compare the last 3 bits of the last state with 3 bit state. If it is matched, then move the directed transition line to the 3 bit state. Else compare the last 2 bits of the last state with the 2 bit state. Then if it is matched, we have to move the directed state transition line to the 2 bit state. Suppose if it is not matched, then again we have to compare the last bit of the last state with 1 bit state. If it is matched, then move the directed state transition line to the 1 bit state. Okay. Otherwise, we have to move it to the reset state. So we have to move this directed transition line state from last state. Okay. That is what the point we have to remember. So then second one is Mealy finite state machine. Here in Mealy finite state machine also there are 3 points to follow. Number one, number of states equal to number of bits of the given sequence. See here, the difference between Moore machine and Mealy machine to have a number of states here is, in Moore machine, the number of states equal to number of bits of the given sequence plus 1. But in this case, in Mealy finite state machine, number of states equal to number of bits of the given sequence. And second point, if the given sequence is a non-overlap type, then we have to move the directed state transition lines from the last state to the reset state upon giving different input bits. And third point, overlap type. If it is 1 bit overlap, we have to compare the last bit of the last state with the 1 bit state. If it is matched, then move the directed state transition line from the last state to the 1 bit state. Similarly, for 2 bit overlapping, compare the last 2 bits of the last state with the 2 bit state. If it is matched, then move the directed state transition line from last state to the 2 bit state. Otherwise, we have to compare the last bit of the last state with the 1 bit state. If it is matched, then move the directed state transition line from the last state to the 1 bit state. So still if it is not matched, then we have to move the state transition line towards the reset state and so on, right? So these are the main points we have to keep in mind in order to draw the state diagram for any kind of sequence detector. Now let us see a problem. problem is draw the state diagrams of Moore and Mealy type sequence detectors with non-overlapping and overlapping that detect the sequence 1001. Right? Now see here, we have to follow all the points that we have seen just now. Now let us consider Moore machine. Given sequence is 1001. Now let us consider Moore machine. Right? So for Moore machine, how many number of states are required? As we have already seen above, that means here we required a number of states. See here, we require number of states in Moore machine equal to number of bits of the given sequence plus 1. So here in the given problem, number of bits are 4. See here 1001. There are 4 bits here, right? So now the number of bits of the given sequence equal to 4 plus 1 equal to 5, right? So the number of states required for this Moore type machine is 5. If it is non-overlapping, then how to draw the state diagram? We have to keep in mind about 3 points that we have discussed in both the machines, Moore machine and Mealy machines. Now let us see non-overlapping type. As we have already seen here, the number of states required for this Moore machine are 5. So that is why we have to draw 5 circles. Okay. Okay. All these circles are representing the states along with their outputs. Okay. So initially we have a reset state. When we press reset button, it leads to a state which is known as reset state. Okay. Which is named as S0. Here there is an output 0. As we have seen in the definition of sequence detector is a finite state machine that receives an input bit stream and generates the logic high output whenever the required sequence is detected. In this problem, the given sequence is 1001. Here in this particular state, the sequence given is not detected. So that is why output is 0. So then when we are giving the first bit as an input to the state, the state moves towards the next state. Okay, that state is S1. Here, if we see, the state also having the output as 0. Because in this state also, the given sequence is not detected. So that is why output is 0. And then upon giving an input 0, then this S1 state will move towards S2 state. Then output is still 0 because the given sequence is not detected. Then upon giving another input, that is 0, okay, the state S2 will move to another state known as S3. And here also output is 0. Here the input is 0. Here we, upon giving another input that is 1, then the state is moved to the last state, that is S4. Here if we see, the sequence is detected. See here, 1001. The given sequence is also 1001. So sequence is detected, that is why output is 1. As per the definition of the sequence detector, here output is 1. So this is how initially we have to draw the state diagram. And then we have to check other inputs also at each and every state. For example, if you consider this state, at this particular state, the input given is 1 already. But what happens if input given is 0? Okay, if input given is 0, then the state will be remain in the same state. Because when we are giving input as 0, the given sequence is not having a 0 bit. So that means the sequence is not detected at. So that is why it is remained in the same state. Upon giving an input 0, it is remained in the same state. Then similarly, let us check at the state 1. Here, when we give the input bit as 0, this S1 state is moved to S2 state. What happens if you give an input bit 1 at this particular state? So in this regard, I would like to explain you something which is very much important. To draw all directed lines very easily, we have to form boxes here. Okay, we need boxes for each and every state. Okay, up to last state. Right? So in these boxes, we have to enter the bits that are detected up to this state 1. So at this particular state, the bit detected is only 1. First, 1 bit is detected in the given sequence, right? And at this particular state, see 1, 0. So that means at this particular state, so 2 bits are detected, that is 1, 0. And at this particular state, similarly, 1, 0, 0. 3 bits are detected, that is 3 bit, 1, 0, 0. And at this particular state, 4 bits are detected, so 1, 0, 0, 1. When we apply input as 1 at this particular state, what happens? Here we have already 1 bit. So when we apply an input as 1, then what will happen? So when we apply 1, 1 1. But 1 1 means sequence is broken. Here if you see the given sequence, that is this is 1 0, but here we are getting 1 1 upon giving an input 1 at this particular state. That means sequence is broken. So that is why we have to now do something, that is we have to compare this last bit with the single bit state. This is single bit state, this is 2 bit state, this is 3 bit state, this is 4 bit state. This bit must be compared with the single bit state. If these two are matched, then the state transition line must be connected to the same state upon giving an input 1. Similarly, let us consider this state. Okay, in this state, we have given an input as 0, then the state is moved towards the S3 state. So what happens if we give, okay, input as 1, then here already at this particular state we have 2 bits in the given sequence, that is 1 0, right? So 1 0 or 1 0 bits are already detected. When we apply input as 1, then what happens? We have to see here, when we apply input as 1, we have to compare this last 2 bits with this 2 bit state. When we compare here, this is having 1 0 bit, but this is 0 1 bit. That means these two bits are, these two are mismatched, not matched. That is why what we have to do, we have to compare last bit with single bit state. Here last bit is 1 and we have to compare with single bit state, that is 1. Now see here, this is matched now. Since it is matched, we have to connect the directed state transition lines towards, okay, this state. Upon giving an input, it happened. Got it or not? Similarly, now come to this state. Here at this particular state, we have already given an input bit as 1. If input bit is 0, what happens? Already this state has 3 bits of the given sequence, that is 1 0 0. If input bit is 0, already we have given input bit as 1, then it is moved towards the next state, that is S4 state. If we give input bit as 0, what happens? Now in this case, we have to again compare this last 3 bits with this 3 bit state. When we compare, it is not matched. So that is why we have to compare this last 2 bits with 2 bit state. Here 2 bit state is having 2 bits, that is 1 0. So here also not matched. So then we have to compare last bit with single bit state. See here, single bit state is 1 here, but here last bit is 0. So still there is no matching. So that is why in this particular case, we have to connect directed transition line to the initial state, that is S0. Up to this instant, that means up to last but one state, this is the procedure we have to follow for all, okay, type of state diagrams. Okay, that may be more machine or melee machine, more machine with non-overlapping or non-overlapping, or melee machine with non-overlapping or overlapping. So in all cases, this is the common procedure we have to follow up to last but one state. When we come to the last state, see here, when we come to the last state, okay, here we need to follow the points I have given above. See here, this is a more type machine. In more type machine for non-overlapping, I have given a point, that is compare the last bit of the last state with the 1 bit state. If it is matched, then move the directed state transition line to that 1 bit state. If it is not matched, then move the direct state transition line to the reset state. The same point we have to follow here, since it is the last state. So here in last state, we have to give 2 inputs. Here in this last state, output is 1 because all the bits that are given in the sequence are detected. So that is output is 1. Even though we have to check this last state with another 2 bits, 2 input bits, that is 0 and 1. Suppose here already in this particular state, the bits are 1 0 0 1. So that means here the given sequence or required sequence is detected. Suppose if I apply input as 0 at this particular state, then what happens? Now in this case, we have to compare, right? We have to compare last bit of the last state with single bit, okay, with single bit state. So now see here, this is 0, single bit state has the bit 1, so it is mismatched. So that is why what we have to do, we have to connect last state to the reset state, okay, reset state when we are giving an input as 0. Got it or not? Next, suppose if you give the input as 1 at this particular state, okay, then what happens? We have to again compare this last bit with single bit state. So here in the single bit state, the bit is 1. Here this last bit of this last state is also 1, so it is matched. So that is we have to move the directed state transition line towards this particular state, which is S1 state. Upon giving an input 1, it happened. So this is how we need to draw the state diagram of non-overlapping Moore type finite state machine. Now let us see the overlapping type in this Moore machine. As I told you already that the procedure is common for all type of machines, whether it may be Moore type non-overlapping or overlapping, or Mealy type non-overlapping or overlapping. The procedure is common up to the last but one state. So that is why I will now just copy and paste the figure. But we have to remove the state transition lines which are connected from the state 4, because for last state, the procedure is different for overlapping case. So when we press the reset button, okay, it leads to the initial state or reset state, that is S0. So initially the sequence is not detected, so that is output is 0. We know that the given sequence is 1001. Okay, see here, upon giving an input 1, the initial state is moved towards next state, that is S1 state. So that is happened upon giving an input 1. And then when we have given an input 0, the state S1 is moved to state S2. And then similarly, when we have given an input 0, okay, at the state S2, it is moved towards S3. Okay, and similarly, when we have given the input to 1, the state S3 is moved to state S4. Okay, when we have given the input bit 0 at this particular state, then the state transition line will be connected to the same state, right? And here, as we have seen already in non-overlapping case, okay, so when we give an input 1 at this particular state S1, then it is connected to the same state, okay? And then here, when we come to the second state, right, when input 0 is given, it is going to the state S3. When input 1 is given, it is going to the state S1, okay? And similarly, when input 0 is given, it is going to the state S0 from S3. When input 1 is given, state S3 is moved to state S4. Now, this is the last state. Up to this state, procedure is common for all kinds of state diagrams. But for last state, procedure is different. As I have given here already that for overlapping case, here we need to consider these points. For overlapping case, for 1 bit overlapping, compare the last 2 bits of the last state with the 2-bit state. Here we see that 1 bit overlapping and 2 bit overlapping. What is meant by 1 bit overlapping and 2 bit overlapping? In the given sequence, there are bits like this 1001. Now we have to find out whether it is 1 bit overlapping or 2 bit overlapping sequence. Here in this sequence 1001, if it is 1 bit overlapping, right, the last bit 1 is the part of the next sequence. Next sequence is also 1001. See here, the first sequence is 1001 and the next sequence is also 1001. But here 1 is common for these two sequences. That is why this 1 is nothing but overlapping bit. So in this case, this is 1 bit overlapping because only 1 bit is getting overlapped. Suppose if it is 2 bit overlapping, I will show you another example. Suppose if the given sequence is 11011, in this case, this sequence is, okay, 2 bit overlapping sequence. Why? Because here last 2 bits, okay, can form a sequence given, that is 11011. See here, for the sequence 11011, here this is one sequence, and another sequence is also found that 11011. This problem is known as 2 bit overlapping sequence. Why? Because here in this 11011, last 2 bits are overlapped. Okay, last 2 bits are overlapped. Okay, and these 2 bits have become the part of the next sequence, that is this 11011. That is why overlapping can be defined like this: if one or more bits of one sequence are part of the another sequence, then it is known as overlapping. Okay, so now the given sequence, that is 1001 in this problem, is 1 bit overlapping problem. Okay, so that is why here we need to apply 1 bit overlapping case. So let us go to the points in Moore machine for 1 bit overlapping case. Here for 1 bit overlapping case, we have to compare the last 2 bits of the last state with the 2-bit state. See here, we have to now compare the last 2 bits of the last state. In this case, for this last bit, in this last state, already there are 4 bits, 1001. Suppose if I give an input 0 then here in this state 10010, we have to compare these last 2 bits with 2-bit state. So what is the 2-bit state here? This is the 2-bit state in which there are 2 bits 1 0. So this 1 0 and these last 2 bits are matched. So that is why we can now connect the state transition line from S4 to S2 when input is 0. Okay. Similarly, suppose if I give an input as 1 at this particular state S4, then let us now see last 2 bits. Last 2 bits are 1 1. These last 2 bits, must be compared with the 2-bit state. Here 2-bit state he is having bits 1 0. So but here last 2 bits are 1 1. So these two are not matching. So that is why we have to check again with the last bit. Okay, we have to check with the last bit. That means we have to compare this last bit with 1-bit state. So when we are comparing, these 2 bits are matched. So that is why we have to connect the state transition line from S4 to S1 when input is 1. Okay, so this is how we need to draw the state diagram for more type machine with overlapping case.
ఈ వీడియో కానీ మీకు నచ్చినట్లయితే లైక్, కామెంట్, షేర్ చేయండి. మరిన్ని అప్డేట్స్ కోసం సబ్స్క్రైబ్ చేయండి.